So here's the unfortunate business for you guys. You're going to groan at first, and then when you realize that this is going to be simpler than an ice table, you're going to be a little bit happier. Okay. Here's the basic idea. Strong acids dissociate 100%, so we can assume 100% dissociation. So we can just assume the hydronium ion and the monoprotic acid are the same molarity. But with weak acids, they don't dissociate 100%. All right. That means that we have to take into account ice tables. Fortunately for you guys, here at LTHS, we have decided to deal with only a small subset of the weak acids, not all of them. Okay. We're going to deal with a subset of the weak acids where the Ka is really, really small, which means that we can deal with it in a special way. When you get to AP, you're going to have to deal with it possibly two ways, but we'll deal with that in a second, okay? The microphone here. This is what I think is the greatest part. Like I said, here at LTHS, we're going to make an assumption about our weak acids. The assumption we're going to make is that the K is going to be so small that when we do an ice table, you can assume that X is so small it's going to be insignificant when we do the subtraction. So we're talking about a situation where X is so small that when you take 0.5 minus X, you still get 0.5. Right. Example, okay? So we've got an example problem where it's asking the pH of a 0.5 molar hydrofluoric acid solution at 25 degrees Celsius. Okay, why 25 degrees Celsius? Okay, but what does that mean we can use? Room temperature, which means we can use what equation? KW equation, the science equation. All right, I like that. We're going to use the science equation. What's that? Okay. So now that we've had the sound of the catastrophic pencil case, this is hydrofluoric acid. Hydrofluoric acid is a weak acid. It's probably important that we write the dissociation equation. So we got HF, reversible reaction, hydrogen ion plus the fluoride ion. Okay. Because it's a reversible reaction, that means that I can write a K expression. The K expression specifically is going to be a Ka expression because this is an acid. It's always products over reactants. So I'm going to put the hydrogen ion and the fluoride ion on top and the hydrogen fluoride, the hydrofluoric acid, on the bottom. The value given on the table of weak acids that I just handed out to you for hydrofluoric acid is 7.1 times 10 to the negative fourth. All right, so, we have to do an ice table. So, initial, change, equilibrium. Ice, ice, baby. Boom, 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 ba-da-dum, boom. Boom, 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 ba-da-dum, boom. All right, then we need to fill stuff in. So I'm going to fill in an initial concentration of HF of 0.5 because the problem said we had 0.5 molar hydrofluoric acid. Okay. All right. We will start out our ice table with no hydrogen ion and no fluoride ion. Okay. A minus X for your HF. A positive X and a positive X for both of your H and your F. Why is what? Because we started out with everything on the left side. The initial was 0.5 on the left side and nothing on the right side. So it can't go to the left. It has to go to the right. All right. At equilibrium, HF is 0.5 minus X, and H and F, both hydrogen ion and fluoride ion, are going to be positive values of X. We can substitute in You might not want to write this down yet. We can substitute in Ka is equal to x squared over 0.5 minus x equals 7.1 times 10 to the negative fourth, right? But I said we're going to make an assumption. Because the value of the Ka is times 10 to the negative fourth, we can assume that it's not going to have any effect on that 0.5. So we're going to instead write this K expression. Okay, notice what happened. Okay, yeah, boom, and boom. If we take away the minus x, do we need our graphing calculator anymore? No. Yay! And square root it. Okay, so we just need to get that 0.5 out of there and then square root it. If we get the 0.5 out of there, we get 3.55 times 10 to the negative fourth, but that's x squared. That means that x is 0.0019 molar. X represents this one and this one, right? So my hydrogen ion and my fluoride ion are equal. They're both 0.019 molar. Now the question said, what is the pH? So we're still not done yet.
Is it 1.4?
Okay, so what we've got to do then is we've got to take, hang on, I guess I should solve for the HF, just in case we need that for some reason. HF would be 0.5 minus x. Technically speaking, we should do that. So it winds up being 0.48. Okay. Then we can say, hey, the pH is going to be the negative log of the hydrogen ion. The hydrogen ion was 0.019, so negative log of 0.019 is 1.72.